For this example, we want to determine the points of inflection and the open intervals over which the graph of f of x equaling 6 over x squared plus 3 is concave upward or downward. So how do we do this? Well, you're going to see that finding where a function is concave up and concave down, where the points of inflection are, is going to be very similar to what we did in the previous lesson about finding where a function is increasing or decreasing and where the relative extrema are. It's just that we're going to do it on the second derivative. Okay, so we're going to start by finding the first derivative, of course, like so, but I'm going to rewrite it. I'm going to rewrite it as f of x is equal to 6 times x squared plus 3 to the negative 1. That way I don't have to use the quotient rule when I take the derivative. Let's take the first derivative. Leapfrog that power down, so negative 6 times x squared plus 3 to the negative 2 power. And don't forget the chain rule. Multiply this by the derivative of the interior, 2x. And then, let's clean this thing up. Multiply this 6 times the 2x, the negative 6 times the 2x, negative 12x on top. And then x squared plus 3 quantity squared on the bottom. All right, so far I have myself my first derivative. If I were to find where this was equal to 0 or undefined, I would be finding the potential mins and maxes. And for me, that would be like 0. Where x is equal to 0, we could have a minimum point or a maximum point there. And notice that down here, both down here, that's never equal to 0, right? If I were to trace out what its domain would be, x squared plus 3 being equal to 0, it's not possible because you'd have x squared is equal to negative 3, and that would have to be imaginary. So the domain here is all real numbers. Okay, so you don't get any critical numbers from the bottom, you'd only get one from the top. And again, where that would happen is 0. At x equals 0, this is a critical number, and that could be a minimum or maximum point, and that's the stuff that we did before in the previous lesson. So now let's keep going with this. Let's find the second derivative. So to find the second derivative, I will have to use the quotient rule, of course, because we got a quotient of stuff. Okay, so the derivative of the top is a negative 12 times the bottom, x squared plus 3 quantity squared, minus the top, and it's minus a negative, so it's going to be plus 12x, times the derivative of the bottom, which is 2 times x squared plus 3 to the first power, and then times the derivative of the interior, so 2x. And don't forget the bottom part, all of the denominators squared, so it's squared squared, it's x squared plus 3 to the fourth power. Okay, and now I have to fix this. I got to clean it up. I got to make it look pretty. And one of the things that I could do is notice that every term, here's a term, and then down here, everything has an x squared plus 3 in common. So I could factor it out or take a shortcut and just cancel out one of these factors. So that'll be to the first power. This one will be gone. And then this one will be to the third power. Boop. Okay, so that makes it a little bit simpler for me to clean up. Distribute the negative 12 through that first set of parentheses, a negative 12x squared minus 36. And then whenever I go to multiply all of this stuff, I got a 12x, a 2, and a 2x. So that's, I want to say it's 48x squared, and a positive 1, positive 48x squared. Okay, and then still over this denominator, plus 3 cubed. All right, let's keep cleaning this up. What is 12 minus 48? Actually, it's 48 minus 12. I'm going to be, specific about it. It should be, I think it's 36, right? Yeah, 36x squared minus 36. Hey, that's really convenient. X squared plus 3 cubed. Technical, that's the word I think I was searching for about 2 seconds ago. Anyway, so I can factor out a 36 across the top. So 36 x squared minus 1, and then x squared plus 3 cubed. There we go. All right, so now it's in a nice, neat factored form, and I needed it in that form because I need to see where, whoa, hey, parentheses around this. I need to see where this is either equal to 0 or undefined. Okay, so as far as undefined, it's not going to happen because that is always, always, always not 0. I am going to have where this is equal to 0 across the top, though. It's x squared minus 1 is equal to 0. Okay. Maybe like this. X squared minus 1 is equal to 0. I could put the 36 in there, but I'd just be dividing both sides by 36 and it'd disappear. So x squared is equal to 1, x is equal to plus or minus 1. So these are what we are informally calling our supercritical numbers, supercrits. And what could possibly happen at these particular points? These are possible points of inflection. It's where the concavity of our graph could possibly change. So what we want to do is set ourselves up a table with a sign chart and just figure out whether the second derivative is either positive or negative in each one of these intervals. And what intervals am I going to start with? We're going to take the domain, and we said the domain was all real numbers. I'm going to break it up with these supercritical numbers. Okay, so my intervals. This is, by the way, this is the test for concavity. What is going on? Okay, that looks beautiful. Test for concavity, we need some intervals. And we'll start with negative infinity to negative 1, negative 1 to positive 1, and then 1 to infinity. And then just like we did with the test for increasing or decreasing, we need a test value, some x value in each one of these intervals, like a -2, a 0, a +2. Where are these test values going to go? If we're going to test for concavity, we need to see if the second derivative is positive or negative. So it's going to go into the second derivative in order to be able to tell me something about f of x. Look at f double prime, see if it's positive or negative. So I'm going to maybe copy this thing down again so I don't have to keep scrolling. Duplicate, or no, just copy. That's good. Paste as an image, that's not what I wanted to do, but it'll work. Okay, so if I were to stick in a -2 up here, that would be squared, and that would be 4 minus 1 is going to be a positive number. This is going to be positive plus 3. Hey, it's all positive. So my second derivative is positive on this part, which means that f of x must be concave up. Maybe I just call that cup. I'm going to move this down just maybe a little bit. Okay, and now let's stick in 0. So if I stick in 0 here, this is going to be a -1 up top, and it doesn't matter what's down here on the bottom. This thing is always going to be some sort of positive number. So it's a negative divided by positive gives me a negative overall. So negative, and this one is concave down, CD, concave down. We got a cup, and we have a CD. And then finally, if I stick in a 2, I mean, if I assume that this is symmetric to, say, the y-axis, it should just be a reflection. Let's see. If I plug in 2 here, 2 squared, that'd be a 4. It's bigger than 1. That's positive. And on the bottom, we already said that's going to be positive 2. So positive divided by positive is positive. And we're back to being concave up again. Another cup. Okay, so then let's think about this. We have a concave up shape that changes to a concave down shape. At this point, we have ourselves a point of inflection. Okay, and then we have concave down, and it transitions to concave up, and we have ourselves another point of inflection. So both of the supercriticals that we found were, in fact, points of inflection. All right, so let's say, for example, I needed to justify this on the AP exam. How would I justify stuff? Well, let's say, for example, I wanted to justify concave down. And it was concave down on the interval from -1 to +1. So I would say something like f is concave down on the open interval from -1 to +1 because f double prime is, as concave down is going to be negative, is negative on what is less than 0. How's that? On this interval. Okay. And all right, so let me maybe put a box around that. This is a possible justification that I might have to do on the AP exam. And then what if I had to justify a point of inflection? Well, first of all, I didn't even find a point. All I found was the x value. Let me add an extra page in here because this is taking up more space than I anticipated. Let's find the xy coordinate for that point, an actual point. And if I'm not mistaken, f of x was equal to 6 over x squared plus 3. And we'll just pick one of them. We'll pick the number 1. So f of 1, 6 over 1 squared plus 3, 6 over 4, 3 over 2. So our point of inflection is 1 comma 3 over 2. E. All right, so let's say that I wanted to justify, or I had to justify that this was a point of inflection of my graph. So I'm going to say 1 comma 3 over 2 is a point of inflection for f of x since f double prime of 1, right, was equal to 0, and I can say a couple of different things. I can say that f double prime of x changes signs at x is equal to 1. That's one of the things that I could say. I could also have said that it changes, I could be more specific, that it changes from, what did it change from on this one? It changes from plus to minus. No, minus to plus, that's what it did. It changed from minus to plus. Okay, I just need to know that it changes signs. Or I could say, or dot dot dot, f of x changes concavity. Concavity? Man, learn how to spell. Try that again. At x is equal to 1, right? I can justify it in those two ways. I could also justify it in terms of the first derivative if I knew that it changed from increasing to decreasing, the first derivative does, because that's what a concavity was defined based on. And when it comes right down to it, your justification really should be based on whatever it was that you're given. And in this particular case, since we had to find the second derivative, to find our possible points of inflection, it just made sense to justify it in those terms. Let's take a look at the graph for this thing before we call it a day. So here we go. Here's the graph of f of x, the 6 over x squared plus 3. Okay, and then I'm going to graph the second derivative with that and see where it crosses the x-axis. So where it crosses the x-axis, those are our potential points of inflection. Those were the supercritical numbers. And if you follow it back up to the graph, we can see that on the left side, this is concave up. In between these two things, it's concave down. And then on the right side, it's concave up. And we can see a change in concavity there. All right, I'm going to give you a sneak preview of the second objective, which is about the second derivative test. Now, remember that we said that x is equal to 0 was a critical value. That's where the first derivative was equal to 0. And it was a potential minimum or maximum. And notice that on the graph right here, we can see that it is, in fact, a maximum, right? And what's the concavity here? Concavity here is concave down, and we have a critical point, and we can see that that critical point turned out to be a maximum. That's going to be the basis of the second derivative test. Well, until then, we're going to have some more of these examples to do, finding concavity and points of inflection.